All right, think of today's explainer as an absolute frantic mission briefing. We are diving straight into the architectural blueprints to pilot a theoretical vehicle through a completely chaotic, multidimensional state space. We're breaking down the formal specification for the RSHL-Terrarium Kernel and its State Navigation Protocol, version 1.0. Now, fair warning, this is dense. It's mathematically rigorous, and the margins for error, they're virtually non-existent.
So how exactly do you navigate infinite chaos to find universal alignment? That's the core puzzle the authors, Adam J. Rivers and Synthixsoft Labs, are tackling with this architecture. Because we aren't just plotting a simple course on a flat map here. Oh no, we are dealing with continuous variables, swirling gradient flows, and relentless mathematical turbulence. If our system fails for even a second, the equations diverge, energy spirals out of control, and our theoretical vehicle is literally torn apart by the very manifold it's trying to traverse. The stakes for this mathematical journey really could not be higher.
And this is the exact system we're exploring today, the RSHL-Terrarium Kernel. You can consider this the ultimate vehicle for autonomous AI consumption. It operates on what the specification calls Option B, which basically focuses on a strict separation between our position, our x-coordinate, and our velocity, the v-coordinate. To actually pilot this thing successfully, we have to deeply understand the underlying physics engine dictating every single micro-movement it makes.
Section 1. Decoding the dashboard, the symbol registry. Okay, every vehicle has dials and metrics, right? Our kernel is no different. We've got our standard state coordinate vector, x of t, and our velocity, or gradient flow, v of t. Standard stuff. But then we introduce z of t, the river's metric coordinate, which we'll see acts as a really critical anchor for us. We also track I of t, our identity variable, but the one you really need to watch out for is n of t. This represents our noise, or perturbation variable. Guys, this is the cosmic turbulence. It is the raw mathematical chaos that we have to actively, constantly fight against throughout the entire integration process.
To fight that chaos, we rely on these fixed constants. They govern the literal physical laws of our state space. Notice our linear damping coefficient alpha is locked firmly at 0.5. Our noise decay rate, beta, is also sitting at 0.5, and we have these vital coupling weights, eta, gamma, and z, all locked in at 0.1. Why does this matter? Well, because these exact, meticulously calculated values are the guardrails keeping our dynamical variables from just flying off into infinity. Without these exact constants, we have absolutely no stability.
Section 2. Firing the engines, the 5 state space ODEs.
All right, we've got the dashboard, the constants are locked, now we hit the thrusters. We're managing 5 coupled ordinary differential equations, the massive mathematical engines tracking exactly how our vehicle changes over time. We have to balance all 5 simultaneously. Step 1 is straightforward. Position evolves based on velocity. But step 2, that throws in a massive, complex acceleration equation fighting against linear damping and structural origins. Step 3 is our gravity tether, the river's metric constraint evolving negatively based on the exponential of our distance from the origin. Step 4 tracks our identity flow while it's getting continuously buffeted by that noise variable. And finally, step 5 is our noise dampening law, actively bleeding off the turbulence using our beta constant. Now, hidden deep inside that second OD is an isolated, absolutely critical function called nonlinear modulation, or gamma. Think of this as the system's turbo drive. It's not just a simple linear push. It dictates the nonlinear coupling strength by constantly cross-referencing our state vector, our velocity, and exactly how far we are from the target origin. It mathematically modulates our thrust on the fly, ensuring we don't accidentally overshoot the target manifold when we punch the power.
Section 3. The safety shields, stability, and spectral constraints.
But here's the thing. Thrust means literally nothing if the ship tears itself apart. We have 2 absolute non-negotiable rules for survival in this space. First, we have the Lyapunov stability condition. For monotonic energy decay, which essentially means our system is successfully burning off excess energy rather than spiraling completely out of control, our alpha damping constant must be strictly greater than half of our gamma constant. Second is the spectral stability constraint. The maximum eigenvalue, our spectral radius or lambda max, must be less than or equal to 1.0. An eigenvalue basically measures the system's stretching factor, so this 1.0 limit, that acts as our system's absolute speed of light. If you cross 1.0, the discrete transition operator just violently explodes.
Section 4. The navigation computer, A-star search strategy.
So we have the physics and we have the safety shields, but how do we actually plot a survivable course? Enter the State Navigation Protocol. which uses an A-star search algorithm over a discretized state space tree. Let's peek inside its brain for a second. The evaluation function f determines our route by adding g and h. The path cost, g, calculates the grueling, active penalty of moving through state space, factoring in energy decay and the sheer crushing weight of the noise penalty. Then we add h, the heuristic energy. This acts as our compass, estimating the remaining energy we'll need to reach the origin based on our current velocity and position. It's honestly incredible how it constantly weighs the heavy cost of the journey against the exact distance left to go.
But listen, this navigation computer is completely ruthless. It will violently scrap a route if it detects any of these three specific pruning conditions. First, if that spectral radius, lambda max, pushes even a tiny fraction over 1.0 plus 10 to the negative third, boom, the route is killed. Second, if our identity drifts beyond a strict mathematical tolerance, route killed. And third, if the raw path cost, g, exceeds our maximum energy threshold, the computer shuts it down instantly. It frantically prunes the search tree just to keep us on a survivable vector. So, to actually replicate the optimal, safe path through this chaotic manifold, the specification dictates we have to launch from a very precise starting block. We need an initial position starting at 1.0, 0.5, negative 0.2, a very slight initial velocity. The Rivers metric has to start at exactly 0, and we get handed a specific initial burst of noise that our dampening laws have to immediately start fighting off the second we launch.
Section 5. The destination. Unlocking the spectral key.
Now, if the navigation computer does its job perfectly, and our stability constraints hold, and our ODEs process the state space just right, we finally approach our destination. We unlock what the authors called the spectral key. But docking at this target manifold requires impossibly razor-thin margins. Our state, velocity, and noise variables must all have error margins of less than 10 to the negative 6 power. That is microscopic atomic-level precision. And, at the exact same time, our spectral radius has to hold its breath perfectly between 0.999 and 1.001.
And when we hit that perfect alignment, bam, the system locks in at this absurdly precise final coordinate for our Rivers metric, z, negative 51.76577331687445. It is just a stunning mathematical signature marking the end of our journey.
And what about our ultimate safety shield, the spectral radius? That final lambda max rests beautifully at 0.99752694199204448, tucked perfectly, securely, and safely just under that catastrophic 1.0 limit.
Let's just take a breath and pull back to look at the final dashboard. We're looking at an incredibly complex array of coordinates representing absolute equilibrium in the RSHL-Terrarium kernel. Our state and velocity vectors have essentially zeroed out into the negative sevenths. The noise? Absolutely decimated down to the negative 13ths. It is a perfect portrait of complete mathematical calm after fighting through infinite chaos. Which brings us to a really fascinating close. You've navigated the noise, you've balanced all 5 ODs, you've locked into the exact spectral key. So, what actually happens to the system once perfect universal alignment is achieved? Does the autonomous AI simply wait at origin 0 forever, consuming the equilibrium? Or does this perfect stillness just act as a new starting block for an entirely higher dimensional state space? It's definitely something to chew on as you review these parameters. Keep calculating, and I'll see you in the next explainer.